The tubes get their name from where the wires go through the studs. So we're going to have a ceramic tube, and then the wires go through that so they don't get damaged by the wood itself in case it breaks. And again, the knobs are going to be those items there. Splices off of these things, and they are mid-air splices. So when we talk about this one first, a knob and tube splice going to another circuit is going to be going to another knob and tube material. And that splice is actually pretty unique on how they did it. These guys were craftsmen, they were artists, they were unique in their trade, basically. What they would do is strip the insulation away, exposing the conductor on the first one. So we're talking about the one that goes through here. And that splice up in there. They would strip away that insulation, exposing the conductor. Then they would take the splice and they would wrap the wire around the original conductor, and then they would solder that joint together. All right. Then they would just cover it up with electrical tape. Now, the electrical tape at that point in time was a cloth type material. They didn't have the plastic, shiny electrical tape that we see in today's stores. It was just old and dull and cloth-like that came in there. So if I saw a knob and tube splice go into another knob and tube circuit with cloth jacketed type tape on it, I would be convinced, or I would assume, and I would have a pretty safe assumption, I think, that was done at the time by the original electrician. And even though I'm still calling out the knob and tube as being an issue, that particular thing somebody didn't do anything hokey with. That's just the way it was done at that point in time. But now if I go to the newer stuff down in here, and here they're showing they put a non-metallic cable and they spliced into that knob and tube wiring. Now I have new wires that come in here, and now I'm trying to splice into the old knob and tube. Chances are that's not going to be soldered together. Chances are it's going to be using the newer electrical tape. And quite frankly, our knowledge has grown since this electrical system was installed. So we can tap off to it. They did make ways to do it. But all these taps have to be in a junction box, all right? We don't do mid-air splices in modern electric with non-metallic cable. We never did. So if I see any sort of NMC or NM cable that goes to a knob and tube, that in itself is going to end up being a problem. So we would want to photograph and document that. All right, needs protection, floor level to 7 feet. That actually goes the same for any NMC. No insulation. That's something that I forgot to mention earlier. These wires have to be out in the open, all right? So if they're running inside walls, I can't fill those walls up with insulation. If they're up in the attic, I can't cover them with insulation, all right? They do need to have clearances, again, 3 inches between themselves or 1 inch to a structure or part of the surface itself, all right? Parallel to each other and intersecting. Yeah, when they go over each other, it's 1 inch. When they go parallel, it's 3 inches. All right, you could stack 2 knobs up when it comes to it. So here's our knob. There's our 1 inch. And what they would do, and I'm talking about this one up here, what they would end up doing if they needed another wire that goes on top of it, they would actually install another knob directly on top of that knob, which would also be another inch up above. All right. Now they took some of these old knob and tubes and they wanted to get some more electricity coming in here. So now we have a junction box. That's the right way to do it. All right. But if you look carefully and you see a little, I think it's a wire coming out of there, out of that junction box at the very top. It looks like we ran a ground wire and the neutral wire, and basically they just brought blank wires coming out of there. And I'm hoping we'll all realize, no, you can't do that. All right. Oh, they did. Here's a close-up of it. And this is the area that I was talking about right here. So that opening is 3 inches apart, and that's where they need to be. This is what the old splices end up looking like. Now, when you come off the splice right away, you don't, obviously you can't get to that 3 inches right away. And what they're really talking about is between the hot and the neutral. All right. So just because it's two neutrals or two hots, they can actually be close together like this. That's not hurting anything. What we don't want to do is allow for something to fall over the top of it. Me personally, I think it should be further apart, but 3 inches is what the rule was. All right. Old splice like that. This means that was done a long, long time ago. So here's a nice picture of our tubes coming through here. And our knobs coming on there. They're not covered with insulation. You can see they did put insulation in the attic, but they left our wires free. Here we're going with either Armor Cable or Greenfield. Once we do something like this, we have to be in a box. And that's about enough on the knob and tube. All right, square D breakers. And more so, we're going back into the panels a little bit. One of the usual suspects that we find doing home inspections are double taps. I want to say just about everyone that we see is going to have 2 wires under a lug. All right. And sometimes it's okay. And sometimes it's not okay. All right. So I'm pretty sure there's other breakers out there that are designed to carry multiple wires under one screw. But right now, the only ones that I ever see are the square D breakers. All right. And I'm going to go to the next slide first. And this is the side view of the square D. So these have 2 plates on it. And then the screw actually pushes down on that plate. So this particular breaker, again, this is the square D one. This particular breaker is designed to carry 2 wires, all right? But it's only designed to carry 1 wire on each side of that screw. If we go back to the other slide, we could see on this one, they put both wires on one side of the screw. That it is not designed to do, all right? So you could put 1 on each side. It is designed to hold that, but not 1 or not 2 on the same side. And again, square D is the only one I'm aware of that does this, all right? Now this code here is actually changing. In Canada, they had it for a long time that switches and outlets all needed to be either 3 or 5 feet away from the tubs, all right? In the United States, they just couldn't be in the tub, all right? So here the question was, an electrical switch must be at least 3 feet away from the bathtub and shower. Originally, that was false. 406.8 says it can't be in the shower space, all right? But this is changing, and this is going to be adopted by more and more municipalities as time goes on, and they are going to be pushing that 3-foot rule to keep it away from the tub. I honestly don't know how they're going to get around some of these things unless, they separate. Obviously, it's got to go. Tub is always going to have to be in the back wall somewhere. Then you're going to have the toilet and the sink in order to get that space. But it is changing, all right? So here in this diagram, the outlet is actually inside of it, and that cannot be in the plane. Once you cross the plane, it's bad, all right? This is on the outside, and again, it just can't be inside the plane. Anything near our water sources should be GFIs, and I didn't really talk about that all that much. GFIs are easy to install. They're cheap. A handyman can really do it. It's light electric where it comes to it. But anything outside nowadays, anything in a garage, anything in an unfinished basement, kitchens, bathrooms, those items should all be GFI protected. All right, plain and simple. This was a I haven't seen Joe in a while. This is a great guy. I'm not even sure if he's still a home inspector. But came to our program a long time ago, and we were looking at a foreclosed house, and somebody decided to put a shower in the bathroom, and we got an outlet obviously inside the shower. That's kind of a no-brainer, all right? This one we saw earlier. Anytime I overload the neutrals, and it is possible to overload neutrals, if I'm sharing that neutral and they're both on the same phase, I can easily run too much electricity than what it's designed to carry. And also, if those wires are loose, they will create a series arc, and that arc will cause the insulation to melt and burn, just like this. So there's more than one reason, I guess, is where I'm going. All right, something unusual that we may see is locks on circuit breakers. A lot of municipalities are requiring fire alarm, sprinkler systems, smoke alarm systems, all of them to be in the locked on position. All right. Now, you're probably thinking, well, if it's locked in the on position and that thing won't let it move, because every time I see a trip breaker, it's actually moved to the middle position. And I can relate to that. I can understand it. But rest assured, this breaker will still trip should there be a need for it to trip. So if I have an overload fault, a direct short, or some sort of ground fault and I'm bonded properly, that breaker will trip. So having locks on them is a good thing. And even, they have lockout tagout kits. And now it shouldn't be locked in the off position. If it is, chances are good there might be somebody working on a system somewhere, and he locked it off so that nobody can turn it on by accident. I would obviously investigate that. If somebody worked on something such as the air conditioner system, they locked it out, they forgot about it, and they're not there anymore, then when your client goes to use the air conditioning system, it's not going to operate because it's locked in the off position. But I think that's rare, and I've never seen anything like that. This is using disconnects or anything that had a separate fuse in it. If they're going to go ahead and run copper pipes, obviously that's not going to work as a fuse, and that's going to create its own problems itself. Overfusing. This is the math that comes with it, and I'd like you to go back to that chart that we wrote earlier. And that chart is pretty much going to be our rule of thumb. All right. So certain appliances, not all appliances, but certain appliances, we can overfuse, and it's still safe. All right. Now this is a rule of thumb. All right. What we don't want to do is rely on this to be steadfast rule that comes into play. But let's take the central air conditioning systems, and for us in residential home inspections, where we're going to see overfusing is typically going to be the central air conditioning system, well pumps, and electric radiant baseboard heat. Well pumps, we're not going to see the data plate, so we're just not going to know what size wire and what size breaker it calls for. Electric radiant heat, not always are you going to see that either. All right, you have to start taking things apart and dismantling them. And we really don't do that to see it. But air conditioning systems, on the other hand, you can see those. All right. And we can take a picture of that data plate that's on there. So the shortcut, if we remember, we had our amperage written first, and then we had our copper conductors and our aluminum conductors. So 15 amps was a 14 gauge. 12 amps, 15 amps was a 14 gauge. 20 amps was a 12 gauge. 30 amps was a 10 gauge. 8 gauge or 50 amps went all the way up to an 8 gauge. So the rule of thumb for us is whatever wire we have there, and that's only specific to those dedicated circuits, all right? Once I start mixing circuits, I can't do this any longer. It's only when it's dedicated. And it's pretty much what we want to do is avoid nuisance trips. We know that when an appliance starts up, there's going to be a heavy draw. and we want to let that draw happen, and then everything's going to back down where it's going to be normal. All right. We can't guarantee that when we have multiple items connected to the same circuit. So this is only for dedicated things. So what we're saying here, the best rule of thumb is you go to the next size larger wire, and whatever breaker you could put on that wire is pretty much what you could have this wire protected at. So if I had a number 10 copper wire, which is typically going to be on a 30 amp breaker, I would take the next size larger wire, which is a number 8, and that chart that I wrote up before, that number 8 says I can go all the way up to a 50 amp breaker. So in this situation, is it okay? The answer is yes. All right, you could have a number 10 wire on a 50 amp breaker. However, what this rule of thumb, like I said, it's pretty much only going to be for well pumps, or it's going to be for electric radiant heat, and there's no way for us to verify that. With air conditioning units, and we could see the data plate, we should be able to tell what size wire that calls for and what size breaker should be on there. All right. So here they allow us to be 175% over, but we can't exceed 225%. All right. This term here, and this is our second to last slide. We'll throw one more up there and we're going to end this. This one here, I refer to this as top loading. All right. So we got a 100 amp breaker, and so the red striped wire has a single 100 amp breaker. The black wire has a 100 amp breaker that comes in there. They're tied together, all right? So even though we have two wires and each one is on 100 amp breakers, again, we do not add these up. This is still a 100 amp service that comes in there. Those breakers will allow up to 100 amps to flow, all right? Whether they're flowing at 120 volts or 240 volts, doesn't necessarily matter. It's going to allow 100 amps to flow. The problem now comes in with that black and white wire that's tied in off the top of this. So those wires also are only designed to carry 100 amps. But now, if those wires, we don't know what they're hooked up to, but let's say they're hooked up to something that's going to allow 50 amps to flow. Now I'm going to be able to allow up to 150 amps to flow down those wires that are only designed to carry 100 amps. Those wires should be after the main breaker and not before the main breaker. This main breaker is not going to be able to sense how much electricity is flowing before it. It only knows what's flowing through it. So if those wires are top loaded like this, we're not going to have the luxury of having that breaker protected, and we could overheat our wires. All right. Last thing I want to chat on is can lights. And then we'll wrap it up, and I hope this all helped you a little bit. So if you do have any questions on anything I chatted about, now's a good time to start typing them in there so I could address them. All right. So there's two different types of can lights. The one we're looking at here is what they call non-IC rated can lights. So IC stands for insulation contact. That means if it's non-IC, that means that insulation cannot touch this can light. Typically, they're painted white. Not always, but typically they're painted white. If we're lucky and we see them, then you could see the old sticker right on there that says, hey, you have to have 2 inches or 3 inches of space around this can light to make it. Now, they do make boots that go ahead and keep the can lights, and I've seen people put boxes around it to keep the insulation from getting around it. But these are pretty drafty as well. And if you have these can lights up in an attic or an unconditioned space, you're going to have a tremendous amount of heat loss coming up through there, because this opening down here at the bottom, I couldn't get down there, sorry. That opening down there at the bottom, that's clearing through. You'll actually see light shining through there. Same thing where this pipe comes through. So once those bulbs start getting hot, heat just goes up into the attic. And once we start heating our attic, and then we're asking for a lot of other problems such as ice damming, moisture, everything else that's going up in there. Not to mention it can't dissipate the heat of these things, so we don't want the insulation touching it. All right. IC rated can lights are typically going to be silver or unpainted. That doesn't mean that they all are. They're, it is what it is. and not always can you tell the difference without seeing a label that's on there. All right. Um, if you put a can light like this in between the first floor and the second floor, so we go in the first floor ceiling, and you don't have any insulation between the first and second floor, that's what they're designed for. That's fine. All right. But once we start putting them in attics or ceilings where the attic above it is an unconditioned space, now we're asking for trouble. And yeah, this is not a good idea. I don't know. So white is typically going to be non-IC. Silver is going to be typically IC rated. And I think that's all I got for you. There is more things with electricity we could talk about, but I am actually losing my voice right now, and I'm just going to call it a wrap. And then I think I'll get some of the interior stuff on another day. So for those of you that are here, I want to thank you. And that is that.